So now you know the capacitance of a parallel plate capacitor. Let's try to recall all the basic formulas that we have obtained in the capacitance. That is, the basic formula for capacitance, it was C is equal to Q by V, that we know. Then the capacitance of a spherical conductor, it was C is equal to 4 pi epsilon 0 R. Now we know the capacitance of a parallel plate capacitor, it is C is equal to epsilon 0 A divided by D. Can you recall the expression for energy stored in the capacitor? There were three expressions. Energy stored in the capacitor is QV by 2, Q square by 2C, then CV square by 2. These were the expressions for energy stored in the capacitor. These are some important expressions that you have to remember regarding capacitor, and we have learned many expressions other than this also. Therefore, at least remember all these things, and these all expressions, most of these expressions are required in our next derivation. The next derivation is we are going to speak about the energy density of a parallel plate capacitor. Energy density of a parallel plate capacitor. For that, what is energy density? Energy density, it is denoted by the letter small u. That is, energy density, it is denoted by the letter small u, and it is the energy stored per unit volume of the capacitor. It's not the total energy of the capacitor, it is the energy stored in a unit volume of capacitor. It is obtained by dividing total energy with total volume. Therefore, let's assume we are having a parallel plate capacitor over here. This is our parallel plate capacitor, and these two are the two sheets. What was the plate area of the sheet? It was A. The distance between the plates, it was called as B. Okay, then as we know, there is three expressions for energy stored in the capacitor. Let me use the expression CV square by 2. I could use the expression as U is equal to CV square by 2. I am using this expression. Where what is C? C is capacitance, and capacitance of a parallel plate capacitor, now we know it is epsilon 0 A by D. We could substitute for C as epsilon 0 A by D. What is V? V is potential. From our previous derivation of parallel plate capacitors capacitance, we know potential is equal to electric field intensity into distance of separation. We have used this expression in our previous derivation. Potential is equal to electric field intensity into distance of separation. Then let's use C and V into this U. Then we could rewrite the expression for energy as C could be replaced as epsilon 0 A by D. There is 1 by 2, this 2. Then V square could be written as E square D square. That is, V is equal to ED, therefore V square will be E square D square. Clear? Then I could write this like this, that is epsilon 0 A E square D square by 2D. 1D and D square can be cancelled. Clear? Therefore, we are having an expression for energy in terms of electric field intensity like this. Then, who's this? It is volume. What is the volume of the parallel plate capacitor? Its plate area is A and distance is D, means volume will be area of cross section into distance of separation. Clear? Then, as we know energy density, it is the energy stored per unit volume. Therefore, we could get an expression for energy density by dividing energy by volume. What is energy? let's use this expression for energy, that is epsilon 0 A E square D by 2. This is the expression for energy. Then divided by volume. Volume is A into D. Then you could cancel this A, D, D. That means energy density U is equal to epsilon 0 E square by 2. That is, you could write it half epsilon 0 E square. This is the expression for energy density of a parallel plate capacitor. What is energy density? Energy density is energy stored per unit volume. It is denoted by small u. You should not confuse that with total energy. Total energy is denoted by capital U, and the expression for total energy, it was Cv square by 2, Qv by 2 and Q square by 2c. From this derivation, now we know the expression for total energy can be this also. That is, you can get one more expression as epsilon 0 A E square by A square D by 2. Okay, therefore these are the expressions for energy stored in the capacitor, and this is the expression for energy density. Energy density is energy stored per unit volume. What is the SI unit of energy density then? The SI unit of energy was joule. Therefore, the SI unit of energy density, it will be joule. Volume is meter raised to minus 3. That is joule per meter cube or joule meter raised to minus 3. Hope you have understood this. This is the expression for energy density of a capacitor. The energy density of a parallel plate capacitor. Next, we are going to speak about dielectrics. What are dielectrics? They are insulating substance which are added between the plates of a parallel plate capacitor. Let me say it once more. Dielectrics are insulating substance which are added between the plates of the capacitor. Why are we adding dielectric between the plates of the capacitor? They are added in order to increase the capacitance of a parallel plate capacitor. That is the new thing that we are going to say. What is dielectric? They are insulating substance which are added between the plates of the capacitor. Okay, there are two types of dielectrics. One is polar dielectric and another one is non-polar dielectric. Dielectrics can be classified into two: polar dielectric and non-polar dielectric. If we are speaking about polar dielectric, let me say the example first. The example for polar dielectric is HCl, CO2, NH3, etc. If we are considering HCl molecule, the hydrogen will be positive and chlorine will be negative. That is, in a polar dielectric, the net charge of that molecule will be neutral. That is, the net charge will be neutral, but positive charge will be on one side and negative charge will be on other side. That means it will have a permanent individual dipole moment. As we have learned, dipole is an arrangement of equal and opposite charges separated by a small distance. Therefore, polar dielectrics, the molecule will have a positive charge at one point and negative charge at another point. Therefore, it will have a permanent individual dipole moment. Then, as the next point, you can see positive and negative charge of the molecule do not coincide. That is, the positive charges on one side and negative charges on other side. Whereas in non-polar dielectric, the name non-polar dielectric is indicating that it is not having any permanent individual dipole moment. That is, if you are taking the example of O2, the molecule's net charge is neutral and the positive and negative are merged together. Therefore, the positive and negative is not separated. That's why we are calling it as non-polar dielectric. It will not have any individual dipole moment, and the positive and negative will coincide with each other. Hope you have understood what is polar dielectric and non-polar dielectric. Then let's take a group of polar dielectric. That is, instead of taking a single polar dielectric molecule, we are taking a group of polar dielectric molecules. This is how the polar dielectric molecules are aligned. That is, they are arranged in a random manner. They are not aligned in an organized manner. They are arranged in a random manner. Then each individual molecules, they are having a dipole moment. Can you recall the direction of dipole moment? The direction of dipole moment was from negative to positive charge. As you have learned it in the first chapter, dipole moment is a vector quantity and it is directed from negative to positive charge. Therefore, this dipole will have a dipole moment like this. This dipole, it will have a dipole moment from negative to positive like this. And each individual molecules are having an individual dipole moment and they are in a random manner. Okay. If you are considering a group of non-polar dielectric, they do not have a permanent individual dipole moment. Therefore, the net dipole moment is also 0. In this case, the net dipole moment is 0. Why net dipole moment is 0? Since each individual dipole moments are oriented in a random manner, the net dipole moment won't be there. Okay. Then, if we are placing the group of polar dielectric in an external electric field, if they are placed under an external electric field, what will happen? Then you just consider an external electric field applied in this direction. If we are placing this same group of polar dielectric under an external electric field, due to this external electric field, the individual molecules will align according to the electric field. That is, over here they were in a random manner, but in this case they are in an organized manner. അതായത് നിങ്ങൾ ക്ലാസ്സിൽ ഇൻ്റർവെൽ ടൈമിലൊക്കെ ഇരിക്കുകയാണെങ്കിൽ നിങ്ങൾ ഒരു ഓർഗനൈസ്ഡ് മാനർ ഒന്നുമില്ല, റാൻഡം ആയിട്ട് പല ഡയറക്ഷനിൽ. പക്ഷേ ഒരു ടീച്ചർ നിങ്ങളെ ക്ലാസ്സിലേക്ക് കയറി വരികയാണെങ്കിൽ നിങ്ങൾ അങ്ങനെ റാൻഡമായി അലൈൻ ചെയ്യുന്നതിന് പകരം ഒരു ഓർഗനൈസ്ഡ് ആയിട്ടുള്ള മാനർ. അതുകൊണ്ട് അണ്ടർ ആൻ എക്സ്റ്റേണൽ ഇലക്ട്രിക് ഫീൽഡ് the individual molecules will align according to the electric field. As a result of that, each individual molecule will have a dipole moment and they are in same direction. Therefore, the net dipole moment is not 0. Therefore, the total dipole moment is not 0. In this case, the total dipole moment was 0. Clear? External electric field is applied in a non-polar dielectric. Then what will happen? ഒരു നോൺ പോളാർ ഡയലക്ട്രിക്കൽ എക്സ്റ്റേണൽ ഇലക്ട്രിക് ഫീൽഡ് കൊടുത്തിട്ടുണ്ടെങ്കിൽ അവരുടെ സ്വഭാവം കൊണ്ട് മാറും. അതായത് ഈ കേസിൽ ഇതുവരെ അവർക്ക് ഇൻഡിവിജ്വൽ ഡൈപോൾ മൊമെന്റ് ഒന്നുമില്ല, പോസിറ്റീവ് നെഗറ്റീവ് സെപ്പറേറ്റ് ചെയ്യാണ്ടാണ് നിന്നത്. പക്ഷേ ഒരു എക്സ്റ്റേണൽ ഇലക്ട്രിക് ഫീൽഡ് കൊടുക്കുകയാണെങ്കിൽ അത് പോസിറ്റീവ് നെഗറ്റീവ് സെപ്പറേറ്റ് ചെയ്യും. They will align as a dipole, that is non-polar dielectric. അല്ല, പോളാർ ഡയലക്ട്രിക് എങ്ങനെയാണോ നിൽക്കുന്നത് അതേമാതിരി തന്നെ നോൺ പോളാർ ഡയലക്ട്രിക്കും നിൽക്കും എപ്പം ഒരു എക്സ്റ്റേണൽ ഇലക്ട്രിക് ഫീൽഡ് കൊടുക്കുകയാണെങ്കിൽ. Therefore, each individual molecule will have an external dipole moment. Therefore, the total dipole moment is not equal to 0. ഇവിടെ ടോട്ടൽ ഡൈപോൾ മൊമെന്റ് 0 ആണ്. കാരണം എന്താ, ഇൻഡിവിജ്വൽ ഡൈപോൾ മൊമെന്റ്സ് ഒക്കെ 0 ആയിരുന്നു. പക്ഷേ ബോത്ത് പോളാർ ആൻഡ് നോൺ പോളാർ ഡയലക്ട്രിക് will align according to the external electric field, and this phenomena is called polarization. ഇങ്ങനെ അലൈൻ ചെയ്യുന്ന ഈ ഒരു പരിപാടിനെ നമ്മൾ പോളറൈസേഷൻ എന്ന് വിളിക്കും. Okay, therefore now we know what is dielectric. Dielectrics are insulating substance which are added between the plates of the capacitor, and the classification of dielectrics are polar dielectric and non-polar dielectric. Why are we adding dielectrics into the capacitor? It is in order to increase the capacitance of a capacitor. Okay.